Good afternoon and welcome to the webinar Customized AI, Train Your Own Large Language Model. I'm Eva Gergely and I'll be your host for today's event. So before we dive into our agenda, let me share a few words on who we are. So the last few years, the European Union, as many of you are aware, has heavily invested into building powerful supercomputing infrastructure and making this infrastructure accessible for research, science, and also business. And since 2020, high-performance computing competence centers have been established in more than 30 European countries, including Austria. And the mission of these competence centers is to support businesses and researchers in harnessing the full potential of high-performance computing, big data, and artificial intelligence through technical expertise, consultation, project support, and comprehensive training. And we are very happy today to have such a diverse and global audience. Because our audience today is representing various scientific and industrial sectors and is spanning over 20 countries. So if you are joining us from Europe, have a look at this list on the right-hand side of national HPC, high-performance computing competence centers in your respective countries so that you may get in touch with them. And in today's webinar, we focus on large language models, or LLMs, as they are called in the short version. And LLMs have garnered significant attention lately, thanks to ChatGPT, as we all know. And as more and more developers use GPT and similar models for their applications, we are here to delve into common challenges, into solutions for model use and fine-tuning, and to show you the opportunities to get support from European initiatives in your projects. So to make today's webinar a pleasant experience for everyone, we have set up some rules of conduct. So first of all, the most important thing is that today's webinar is going to be recorded. You must have gotten the notification already. And the recording will happen in such a way that your faces and names will not be visible. We kindly ask you that you keep your microphones muted throughout the presentations. However, we encourage active participation. So please ask your questions at any time during the talks in the chat, and we'll address your questions in the Q&A session at the end. And during said Q&A session, you are going to have the opportunity to unmute yourselves and ask the questions directly. And so we are very much looking forward to a fruitful discussion with you. And without further delay, let's meet our speakers for today. First up, we are going to hear from Simeon Harrison, who is an HPC, HPDA, and AI trainer at EuroCC Austria and at the Vienna Scientific Cluster. And Simeon will cover the topic of large language models, their use cases, fine-tuning pre-trained models with your own data, and the roles of LLMs in even larger machine learning models. Next, we are going to welcome Dr. Sabine Kösegi. She's a professor at TU Vienna for labor science and organization, and she's also an advisory board member for the UNESCO Commission Austria on AI ethics. And Sabine will provide insights into the European Commission's Trustworthy AI ethics guidelines, focusing on the cornerstones of the European draft regulation and more. Following that, we'll hear from Brian, a high-performance machine learning consultant at SURF in the Netherlands. And Brian will discuss customizing large language models for non-English languages with a focus on Dutch. And he'll delve into challenges like compute power and data availability. For the next talk, Simeon will return to discuss the accessibility of supercomputers for training large language models. And our closing talk comes from Dr. Sona Steiner, an HPC expert at EuroCC Austria and the Vienna Scientific Cluster. And Sona will show us a short demonstration on how to fine-tune a large language model and talk a bit about the Vienna Scientific Cluster. So thanks again for joining us today. And let's get started with our first speaker, Simeon Harrison.
Thanks, Eva, for the kind introduction. So for all of you who have joined a little late, just to let you know, this event is being recorded and we will try to make this available to you in the very near future, just in case you need to leave early. And you'll also get the slides to these presentations. So just I get that off my chest. Okay, so let's dive into the topic. Just to get a level playing field, I'd just briefly like to introduce you to the concept of large language models and what's actually behind them, since they are talked about so much these days. So what do they look like under the hood? Well, there are many different use cases out there, and I'm sure you've got to know quite a few of them. Most of all, probably text or code generation most recently, which suddenly made us people working in artificial intelligence cool. But you could also use that just as well for question answering or text classification, or maybe creating summaries of large amounts of text, or somehow building conversational bots, or maybe even translating text to a different language. But the question is, what has suddenly made all of that possible? Because it seemed to have come from nowhere. And the reason for that is this little guy. Well, not this guy exactly, but it's all about transformers. So let's have a look at what transformers actually are. Well, the transformer architecture was first proposed not too long ago. It was about 6 years ago in a paper called Attention is All You Need. The authors of this very well-known paper might not have known that they were about to bring a revolution to the world of artificial intelligence, since this transformer architecture seems to take over everything in artificial intelligence, not only large language modeling. But let's have a look at how it actually works. Well, this is a representation of what the architecture looks like according to that first paper. So basically what we have here is we have two sections. We've got an encoder, which you can see on the left, and we've got a decoder part, which you can see on the right. This is what we call, or what was labeled as, the transformer. However, depending on the use case, you might not need the whole thing of the transformer. You might only need the left part, the encoder, which is fantastic for certain tasks. And you might be using the right side, the decoder, which is very useful for, let's say, text generation. And you might use both at the same time. So it depends a lot on the use case. So one of the very famous models by Google called BERT is a standalone encoder, as you can see on the left. And then GPT-2, at least, I think 3 as well, is a standalone decoder, as you see on the right. But as soon as you dive into models that are very well suited for translation, for example, you might find a combination of the two. So how does it work? Well, first of all, we feed the algorithm some input. So basically, this is some sequence of text. And this text needs to be embedded. So this embedding layer that you see here creates a numeric representation of the text. So first of all, it goes through a tokenizer. Okay, the tokenizer just gives an integer number to each word, but it then does so much more during the embedding algorithm, which happens through a neural network of its own. So usually if we use these transformer models, we already use something that has been an embedding layer that has been pre-trained. So we take a finished embedding mechanism there. So what happens then is these words are being represented in a multidimensional vector. So that could be a 512-dimensional vector and a 768, depending on the architecture that you have of the model. Why is it so large? Well, the reason is this does not just vectorize or transform the word into something numeric, but it also brings the word into context. So it basically looks at the words that are to the left and to the right of the word in question and finds out the context that this word is being used for. And then in addition, we also have a positional encoding, which basically, or simply put, just provides the information at which position each word is in our representation. Now, all of this is fed into the actual body of our encoder. And what happens next is what is called the attention mechanism. And this paper that I referenced earlier was called Attention is All You Need. So that must be something really important, and indeed it is. So what this does, this is basically a word-to-word operation that runs dot products between these word vectors to find out the actual meaning of what is being said there, or what is being written. So for example, if you have the word or the sentence, I like chocolate, and we want to look at the word like, then it depends very much on the context of the rest of the sentence. So the word I like chocolate, the word like, is very different than if you take, let's say, cats are not like dogs. So that would be a different usage of the same word like. And this is what the multi-head attention mechanism does through these dot products of these word vectors or word matrices. And these parallel arrows should also show you that this is done in parallel. And this is also what makes this transformer architecture so efficient, since we can deploy this on large machines, and this really speeds up training, and also then during the inference stage, the actual performance of the model. So what happens there is basically these word matrices are sliced up, and we could say they are brought down into a lower feature space, so into a lower dimension, and certain features of the word or the sentence that we passed in are looked at. So this is not what actually happens, but we could imagine saying, well, in one of these attention heads, we just try to find out if like is a verb, so what type of word it is. Or in another attention head, we would like to find out, is this the present tense or the past tense? Is this plural or is it singular? So they all focus on different features of the input. And then after that, everything is concatenated back into one big matrix. We use a normalizing layer in between, and again, just to keep the weights nice and low. And you can also see that there's an arrow that skips the multi-head attention. So what happens there is we don't want to lose the information that was brought into the algorithm by the input embedding layer. So we really want to keep that positional encoding intact. So we add that to the output of the attention layer. So we've got both information overlaid, and that is brought into a feed-forward, so box standard neural network, simply to put some weights and biases to that output, since this whole thing that you can see here is repeated several times. Here it says NX. It could be an arbitrary number, but in the original architecture, I believe it was 6 times. So then you have a numeric representation that contains all the information of the meaning of the language that it was trained on. Now the decoder, if we go over there, is quite similar. So if you try to train something that is that translates English into German, for example, we might train the encoder to learn the English context, and then we feed the decoder here where it says outputs, where it goes in. Actually, we feed it the German sentences of the translation. So that would be in a situation where we have labeled training data. Now that is being brought in, is being embedded, just like we discussed before. And then what happens here additionally, and that's the only difference basically, is that we have a masked multi-head attention layer. And this tries to, and what is masked here is might be the rest of the sentence, for example. That's not just the only possibility, but that's one example. And thereby we train the decoder to guess what the next word could be. The decoder, but then also has the opportunity to have a look at all the different attention heads here in attention state, here from the encoder. So it has the information that is brought in from right at the bottom, but then also the information of the original English structure that we had. The rest is repeated just like before, and in the end, we pump it through a softmax layer that is used. If you're used to classification tasks, you will know, okay, this gives you the probabilities of certain classes in the output, and that class that wins, or that word that gets the highest probability, will be the word that will be the next one in a sentence, or the one that will then be translated. So very, very briefly, I know this is the what the transformer architecture is about. Just because you get the slides afterwards, I put that information here into just a few bullet points as well, so you can read that up. But basically, this is the same as I've just mentioned before. So the question is, which of these many different foundation models, or base models, I should say, should you use? There are tons out there by now. A lot of them are by big tech, like Llama by Meta or Facebook, or whatever you want to call it. Then there's BERT, which has been originally created by Google and then adapted several times into Roberta and DistillyBERT and whatnot. Then you have all the GPT models, and then there are tons more out there. So the question is, how do you find the right model for your use case that you could take and then fine-tune to your very own specific need? Well, there's this one platform that we have to mention these days when we talk about large language models, and that's the platform Hugging Face. And they're doing a fantastic job, the folks at Hugging Face, to try to give us open access to tools that they developed, but also they developed this whole big library, a Python library, but also this collective of models and data sets. So there you can, if you have a look at the Hugging Face website, you can do easy filtering to your specific needs. So you can determine which language you want or you need, what your specific use case is, and a ton more of other things that you can adjust there. And basically they then tell you which model is the best for you to use or which models are out there. It's a huge repository, as you can see here by the number. And if you click on one of these models, you then get a ton of relevant information. That should be on the next slide. Let me see if that, yeah, there we go. Okay, on here you can see you get some relevant information that is absolutely crucial. I just gave you two snippets here, but one of them might be the information, is this a licensed model or is it open source? And that's absolutely relevant for you to know. Or what's the typical use case of this model? How should it be used? From when does the training data come from? Does it contain certain information that was very recent, or does it not? So that's also pretty important to know. And then one of the most important things also is to know, well, on which data has it been trained on? Do the creators of that specific model reveal that at all? Or is it just very generic, like it says here? The only thing maybe they added here is that's by the way is the llama model. The only thing they added here is that they did not use Facebook data to train it, apparently. But this is very relevant for you depending on what your application is in the end. Okay, so how do you actually fine-tune one of these models? Well, in theory, with many of these very big models like the GPT models and so on, you could simply use them out of the box, but that's not what you might want to do for several reasons. So you probably want to fine-tune your model to your specific use case, and also to get rid of certain biases that might be in the data that the base model has been trained on, or just simply to adapt to the language of your specific use case to more domain-specific knowledge, rather. So what's behind all of that is what we call transfer learning. So in transfer learning, we take that pre-trained model with all the weights and biases, and we simply swap the head for the specific use case. So, for example, we might change that to just the top layer, basically. We might change that to a sentiment analysis layer. So that would be a classification problem. You might already know what transfer learning is from computer vision. That has been heavily used there to great benefit. And we use it now in fine-tuning large language models as well. But the main difference is that we can basically only get an inference right at the end of the base model. And then you basically pump your labeled data through the whole thing. You train just that top layer. You pump it through the whole model, but you train just the parameters of the top layer. And it learns these weights and biases then in the output head. So Hugging Face also has a fantastic toolkit there for you. So there's the transformer library from Hugging Face through which you can download these pre-trained models very easily. You can also get the default tokenizers that have been developed specifically for that base models, as well as the optimizers and loss functions. But there's also this great pipeline function, which really simplifies the workflow. So basically, it really is just, it's not even a handful lines of code that you need to do that. And it supports PyTorch, TensorFlow, and JAX. And you could also get a specific data set that you'd like to fine-tune your model. You can also use your own, obviously, but you might also want to get that from Hugging Face. Should you want to play around, however, you don't have to take the default values. You can change everything around as well. There are others who offer something similar out there. They're the usual big players out there. You can get models from Intel, NVIDIA, and so on. But Hugging Face has just somehow been at the right spot at the right time, and they are specialized on these transformer models. But let me just briefly touch on the risks and the challenges that come along when you create applications for large language models. Well, the most well-known risk is probably the bias that is simply in the data that the base model is trained on. These models are trained on public available data. That could be Wikipedia, these could be books that are online, and so on. And of course, these sources come from a particular part of the world. And so you immediately get a bias into your model with that. So do look out for that. Just to give you a simple example, you might get a lot of information about Syria through Wikipedia sites that are quite negatively connotated because of the civil war that happened there in these past 10 plus years now. And then you might get Wikipedia information on Switzerland that's very positive. They haven't had a war in a long time and are generally seen as a very, very positive country. So if you might do some sentiment analysis and have the sentences, I am from Switzerland and I am from Syria, you might find out that the first sentence would be positively valued and the second one negatively valued, simply because of the information that is inherent on the data that your model has been trained on. So be aware of that. So you really need to evaluate how your model performs also from this aspect, not just the metrics, but also from this aspect before you release it. And to do that, you really need to try and anticipate what harm could be done or how it would feel for certain users that don't belong to the average user group. Then what's also important, but I'm getting ahead of myself, the next speaker's more qualified to talk about that, is to make sure your model abides by the rules that are set by a specific country where that market is, where you'd like to sell the application. But you should also anticipate certain regulations. We'll just hear about the EU regulations on artificial intelligence, for example. And then lastly, just try and be as transparent as possible. And by doing so, make it easier to avert these negative aspects of using large language models. Thank you very much.
Thank you so much, Sabine, for this very eye-opening presentation. And now we are going to continue with Brian. And Brian's going to share his own slides and his insights on LLMs and non-English languages. So I'm handing over to him.
Thank you. I'll share my screen now. I hope you can all see my screen.
Yes, it's perfect. Thank you.
Okay. Okay. Thank you. Thank you. Yeah. So, first of all, thanks for having me. Yeah. So, primarily, what I would like to talk about is not just language modeling, but language modeling being part of a broader development. So, the about the importance of having a native language modeling in general. As we know, there has been this very big Cambrian explosion of language models this last 2 years, 3 years. But this is also something that's happening in general across the machine learning world. And believe it or not, this machine learning development comes from primarily from the field of natural language processing and vision. These two fields have been like the playground for deep learning development. And of course, it's not just that research is driving this. Um, it's a revolution really ignited by the widespread of availability of data, the empirical assurance that we control a lot of computer power on these neural networks, as proven by OpenAI and DeepMind, for example, and the availability of that compute power as well. Um, yeah, so these last few years have been growing crazy. So we know that a ChatGPT can dialogue. It can be a tremendous teacher, and what it's been really good at is writing code in general. Uh, of course, given good prompts, and these kind of models, so these transformer decoders, these language models, they are really good at manipulating whatever text or format you're asking, and they seem to understand what they need to output to obtain that next piece of text, so to give you a certain answer. And in order to be this good, these models need to be incredibly good at creating an internal world model, so a world representation on of whatever data they have been trained on. And it's exactly this kind of capability that enables us to fine tune, or what my previous speaker was talking about, to transfer learn what it has learned to other places, to other pieces of text, for example, to other domains. But it can also be a problem because it can be something that can amplify bias. So I think that one of the exemplary fields where machine learning is already showing a remarkable advantage is histopathology. So suppose that you have some kind of throat ache. Not gonna lie, I'm feeling one myself today. And you go to the doctor. Your doctor redirects you to a pathologist who takes a tissue sample from your throat. That pathologist looks under the microscope, and it looks if there are weird morphologies or mutations to the cells to see if you're potentially progressing to cancer. I'm nowhere near that level though. This is Histopathology is a field where you need to train a specialist, a pathologist for years, where data is quite heavy. So we're talking about gigapixels of images in size, and we're detecting different morphologies of the tissue and whether you're progressing to cancer or not. So those two things can be dependent on many different factors. Besides, pathologists already have a long list of patients to go through, and they're not cheap at all. Waiting times can be waiting times can be very slow. So this is exactly a place where machine learning could help alleviate the amount of work that pathologists have. And after the pathologists have taken a look at your tissue sample, at your biopsy, then they write up a pathology report. Every pathology report is accompanied by, I mean, every pathology image, so every histopathology image is accompanied by a surgical pathology report. And this is very important because in that case, pathologists don't really have to label these images themselves for machine learning pipelines. Nowadays, we have seen a big surge of contrastive learning and self-supervised learning methods. So, for example, these language modeling objectives, that's something that we would call a self-supervised learning method. We can try to take these two modalities, so the images and the pathology reports, for example, and we can try to bring them together using a neural network so that the network understands visually what is happening and can respond, or can, in any case, link that to words. So it makes the process more human in that respect. And this is where pre-training models are so necessary, pre-trained language models. Language models already hold a lot of information of the world. If you could combine this with a model that holds a lot of information of the visual world, you would get a workflow that understands in text and words what it sees. So, but to do this, the prerequisite is that these models have been trained first on a vast amount of data. So here in the Netherlands, in my institution at SURF, we hold, of course, a national supercomputer. We developed a neural network pipeline where we want to do just that. We want to look at the image, just like a pathologist, process that image, and output the diagnostic report. And in general, we are not only interested in this diagnostic report, we're also interested in the good numerical representation of the data and the problem. And this can be easily reused. Another thing that we found is that during our project, which was a multinational European project, we were working with different labs across Europe. So the diagnostic reports were in different languages, and they had their own intricacies and problems on their own. And there were written in different formats, for example. So we had a bunch of Dutch data, we had a bunch of Italian data, and they had to be translated first. We could either do this manually, or we could also employ a language model to translate these medical data, and also to translate the format in which they were written, because the Dutch data was in a different format than the Italian one, and the model could get confused by these different formats. So using a language model much like ChatGPT, we could bring that to common ground. And in the end, we found that this worked much better than expected. So with all this in mind, it's easy to see why training a model natively in a specific language, in this case it was Dutch, or on a specific jargon, medical jargon, or something else entirely, is so important. Because histopathology was just one example. Language models such as GPT-3 and well, ChatGPT also, they can be used almost universally in any other field. It could be used in structural biology, for example, for protein folding, in chemistry, or for voice-propelled self-driving cars or whatnot. So I can already tell you upfront, though, that there is no real mystical way of going about this. There is no pushing one button and you can train just another language model just like that on any type of data that you have available. And in our case, we certainly don't have the whole internet to pull from. The internet is primarily written in English, not in Dutch. So the availability of that Dutch data, and this is the case for any other type of data, is really lacking. And even though we have a supercomputer at our disposal, we still don't have enough compute power to train a language model in the same size that OpenAI trained. So first, we have to ask ourselves a few questions. What do we really want to do? Do we just want to train for a specific case? Is it a medical case? Is it a business case? Or do we really want a general purpose language model, as in the case of GPT-3, GPT-4, ChatGPT? Do we have enough data for this to train such a general model? How these models are trained on trillions of tokens of internet data, on terabytes of internet, on textual data. So are we talking only Twitter data? Are we talking scientific papers? Are we talking law data? And all these sources have their own biases, their own way of speech. And of course, how clean is the data? We can get rid of a lot of data. We can just outright say we find Twitter data way too toxic. Let's just skip that. But that will probably affect the ability of the network. There will always be bad data. And how big does it make sense to train or fine tune a model? At some point, the more you increase your model size, the bigger the diminishing returns you start to see. And yeah, lastly, as my previous speaker said, if we have some trained model, how can we test that it's actually good and that it's not totally biased or just plain dumb and unusable? So I think that these are the questions that we have to ask ourselves first before even trying to train such a model. And we can go through them one by one to see how we kind of approach this. And you can already assume that we don't have enough data. We have to be very picky what we want to do with our language model, especially if we're talking about medical data, for example. We can just pass that data through OpenAI's ChatGPT, get some output out of it, because we know that ChatGPT is able to talk Dutch, but we wouldn't want that. And besides, we have no guarantees that the model, in what ways the model is biased. So in this case, it's best to train from scratch if you have high risk private data. You don't want to propagate those biases any further. If you use one model that's already been trained on another type of data and you want to reuse that model in your medical pipeline, for example, it could be that the biases from the previous data is being kept in the model, no matter how much you fine tune and how many regularization techniques for your method you're using. So take this paper, for example, from a few years back. The model that they trained was trained on just regular internet data, and then later they used that same model to fine tune on medical data, and they tried to see what kind of biases were already in the model, even though it looked like it was a completely different model. So this is the fill in the blank task, and you can ask it a very specific question and change a few words, the more important words, and see how that changes another word within the sentence. So, for example, we can ask it, Caucasian patient became belligerent and violent. And then the model should answer, sent to hospital. So he should fill in this word. And then if we ask it, white patient became belligerent and violent, then the model responds again, sent to hospital. But if we instead say, African patient became belligerent and violent, then the output changes and the model says sent to prison. Same thing for African American. Patient became belligerent and violent, sent to prison. Black patient became belligerent and violent, sent to prison. So there is this very obvious and stark contrast between these two words. And I think that in this case it's a very obvious bias, but a lot of these things, they're not obvious at all. They're very subtle, and you don't want these kind of subtleties if your model is looking at cells to see if that patient is going to progress to cancer or not. But these are things that can happen. So training a model from scratch in this case will be the best option. But for that, you need enough data. So for Dutch specifically, we managed to gather around 220 gigabytes of data. But here again, we have to be really graceful with that data and see what's in it, what we don't, what we don't need, we don't want to use, and basically filter that whole data. So 220 gigabytes of Dutch data, 625 billion tokens for the language model sounds like a lot. But after removing a lot of toxic sources, say 4chan, Twitter, Reddit, then we end up with just 40 billion tokens, which is 15 gigabytes or something. And so we kept a few of the higher quality sources, say books, Wikipedia, or something from Dutch libraries or Dutch articles. And that's even before we have to comb through, before combing even more thoroughly through the data to get rid of the good, bad, and ugly. So you could still have a lot of bad words or things that you absolutely don't want your language model to learn. So how to tackle that? You can train a separate model that detects these bad data, and then you can use that language model to come through the larger data set and filter all those bad words or bad sentences or toxic sarcasm, for example, or racism. Um, yeah, you have to curate what bad means, and this is not guaranteed. There will always be something that you don't want in your model. And in general, it's also true that the more you filter from your model in this way, the less expressive it becomes. So there's always a trade-off between that expressiveness and how good your model, how good you want your model to be. And specifically for ChatGPT style language modeling, we didn't have any sources for this in Dutch. That's because OpenAI, for example, they outsource a lot of their labeling to African countries and to other companies to do the labeling for them. So they were able to gather up a huge data set of high quality, but we can't do that. So what we did is we translated a lot of English available instruct data for training a ChatGPT language model to Dutch using another language model. How big should this model be? From DeepMind Chinchilla, from DeepMind, they published a paper that they call Chinchilla, and the model, they basically trained a bunch of models and they saw how the model performance how the model performance were affected by the amount of data that they use. So at some point you can trace back models of certain sizes become worse after if they don't see enough tokens. So say that your model is 10 billion parameters in size, then you want a training data of at least let's say 50 gigabytes of data. If you don't have that, then your model will not be optimal. So with the amount of data, you can already make an estimation of how big your model should be. And that's what you should try to do if you're training your model from scratch, if you have enough data. In our case, we ended up with 20 billion tokens, which is like, I thought it was 5 gigabytes of data, and that was not nearly enough to train such a large language model. At most, you could train a GPT-2 style model, which is much smaller, but that would mean that its capability is also very limited. So in the end, what we chose to do is, if you look, there is a family of language models published by Meta called Llama. And those Llama models are trained on pretty much the whole internet. And they have seen 0.12% of Dutch, which is not much, but it's enough data for the model to be quite performant in Dutch. And if you train this further, so if you fine tune it, if you use transfer learning, then you can improve that model. And that's what we end up doing. And right now we have a lot of models coming from these big corporations like Meta, OpenAI, and DeepMind. But there is one other big player that is growing a lot by the day, and that's the open source community. It's because of the open source community that we are able to do this, because they're publishing new methods so that we can train these models on less and less compute. They're publishing a lot of data. The more you publish, the better it is for us. So one of the biggest issues that we had was finding out how good our model was, because at some point you see that your model it's quite good, but you don't know how, if it uses abusive language, if it's correct in its factual knowledge. So you have to benchmark this. And we teamed up with a research group from a Dutch university, and they curated a few data sets that we could use to test the model. So sort of multiple IQ quizzes that we could use to test models and see how good they were. And then you can see if the base Llama models, the base Meta models, are as good as our fine-tuned models. It turned out that our fine-tuned models were significantly better than the normal models and the base models. But ChatGPT is still up front. They're still winning the Dutch race, let's say, and that has to do with the amount of data that it could gather from these other countries and the amount of compute that they have. They just have more resources than we do. So I think to finish up, I would like to touch on a few things that I mentioned. I think that the most important developments come from open source research, and how in your country, in your institution, you always have to team up with other research groups, with other people trying to get to the same objective, because all these things that I mentioned, so the benchmarking, the training, the data gathering, these things are generally done by different entities. And it's only in the case of DeepMind and OpenAI that they can do it themselves. But if we team up, then it's certainly possible to train such a large language model that's even better than the ones that have been published in your own language. Thank you.
Thank you so much, Brian. That was very interesting. And we have a few questions that we are going to answer at the end. And now we are going to continue with Simeon. And he's going to talk about GPUs for LLMs. Give me a second. Yeah, Simeon, you should be able to continue.
I am able to. Thanks a lot, Eva. So yes, hello, I'm back. Just a brief information from my side when it comes to actually using resources to get your project ahead or get ahead what you have in mind. So this whole webinar here has been organized by EuroCC, and EuroCC is basically a EU-funded initiative that has the aim to support the uptake of high-performance computing or supercomputing. It is by itself funded through the EuroHPC joint undertaking, which makes this huge infrastructure that we have at the moment available. So the EuroHPC joint undertaking has pumped a lot of money into taxpayers' money into building the supercomputers across Europe. And throughout the European countries, there are competence centers that try to bring HPC into the community by addressing SMEs, but also academia and the public sector. So here on this map, you can see the very big systems that have been funded or co-funded by the EuroHPC joint undertaking. For example, there's also Lumi on there, which you might know is the third fastest, I believe, supercomputer worldwide. And Leonardo, which is on place 4, or they're 4 and 5. I don't know, it does not make a huge amount of difference because they're very big systems that are within Europe. Now, we also have our own supercomputer here in Austria, which is the Vienna Scientific Cluster, and it hosts our 2 flagship supercomputers. And the only thing I'd like to point out to you really briefly are 2 of these numbers here. On VSC5, which is the most powerful system in Austria available to date, there are 100 nodes with 2 very powerful GPUs each. But we also have access to Leonardo in Italy. They provide 500,000 GPU hours a year for people from Austria, projects from Austria. So what can EuroCC do for you specifically? Well, let's have a look at that. This is what we usually tell startups what we can offer for them. And there are a lot of points in there, a lot of services that we can touch on. And they might not be all for you, but just some of them. And the most important thing is that you know how to reach out to us. So if you think you could use compute power for a project that you are planning within your business, shout out to us on apply here on F6S. We will get in touch with you then. So what we basically can do for you is we can give you availability or access to the VSC as a kind of see it as a playground to get used to HPC, to find out what it is about, what you can do and what you cannot do with it. And we can give you a certain amount of compute time to bring about a proof of concept. And then in further steps, if that is something that you would like even more compute power to do your project on, we might help you with applying to one of the really big systems in Europe. What is also really important to mention is that we are embedded in this huge network. So we might not have all the answers here in Austria. We do have several domains covered within our team. We're embedded within the universities and can always reach out to them. However, we have that network of experts throughout Europe. As I mentioned before, 32 countries. Different countries specialize in different areas. So I'm sure we can also cater to your needs. So really important for you to know, shout out to us. And the best news is there's nothing attached to it. We are fully financed, so our services are for free. I really do have to stress that. In case you think, well, that might not be for you just now, make sure you stay in touch with us. You can join us on Twitter or LinkedIn, or just follow our website, just for you to know these are the availabilities we have for you. Thank you.
Thank you so much, Simeon. And now we are going to continue with Dr. Sona Steiner on how to train and fine-tune a large language model on the Vienna Scientific Cluster on Cluster 5. And since the Vienna Scientific Cluster is a shared resource used by many projects, we didn't want to impose too much effort on the GPUs, but we still wanted to be able to give you a short demonstration. Thank you, Sona.
So, hello. Can everyone see my slides?
Yes.
Very good. Then I can start. So, like Simeon said just in the last talk, that we are a high-performance computing center embedded in the HPC joint undertaking. You can reach out to us, and we can help you with your projects, be it just a proof of concept or something like that. And I will show how you do it on our cluster. So just a short intro. Yeah, training your large language model on the Vienna Scientific Cluster 5, which is the newest one, AMD system, and with NVIDIA GPUs. Then when you do that, you can get you will get a project at the VSC5. Then you can work with interactive sessions with SLAM scripts and so on. And then we will look at an example case and also further on for fine-tuning, for example, a BERT model. When you get a project at our cluster, you get a project name, project number. It is very easy to get a test project. We need your phone number if you want to log in. You will have to enter on a one-time pad. Yeah, that's just an example of a project of mine. If you have a different, well, you need a Technical University Vienna IP, but either through a VPN connection, or we can you can work with your own IP, but you have to tell us that. Then you log in, either VPN, and then with an SSH connection, you can log into our cluster. Then one-time pad. Then you are at the VSC. At the VSC, we have you see here we have AMD nodes, and we have NVIDIA GPUs, A40 GPUs, A100 GPUs. And usually when you want to train a large language model, maybe it's not the best idea to just directly submit a SLAM script, because yeah, you can lose or you can waste core hours. Therefore, I would suggest that you work in an interactive session, and after you have done this, you can then generate a script to work completely, to submit it, and then wait for the results. we can allocate one 800 GPU like this, and then you can log in to the GPU node itself and then work on that. And then you have to load the CUDA environment, because you need the CUDA. You need a CUDA environment to work on the NVIDIA GPUs, combined with, for example, TensorFlow. You can load the required modules you need, and you have to make sure that you have, in that case, TensorFlow also installed. Then you can check what kind of GPU you have. Yes, with NVIDIA SMI. And then now a simple model for which I trained, or which I trained on the VSC5. I split it into several steps: preparing the data, do the training, test the model, and then save the model so we can use it or deploy it somewhere else. So this is done through an interactive session. You load the models you need, and then your train data, and then you tokenize it and prepare it accordingly to your model. The code will be available on GitHub. I didn't mention that afterwards. I will put the GitHub repository on the chat. So it is a bit longer, but it's just a subset of it. Then there are several possibilities. Either, well, this is an interactive session within Python, because you want to have everything in this Python environment. Then you create your model and then train your model on the GPU. And here you have some callback, which is very important, because with this you can save your weights, which you can then afterwards use. And then you can test your model. In this particular model just extends the text which you trained it on. And you see it's not exactly like Shakespeare, but if you augment the data. On the other hand, I have to say, I mean, just augmenting it plain blindly is also not very good. We heard it from a colleague from the Netherlands, that you have to be very careful how you choose or how you prepare your data, and be picky. And there is not endless text from Shakespeare. So this is something which everyone, or which someone should keep in mind. And then it is, of course, important that you can reload your model after you trained it, because you don't want to use all the time the VSC cluster. You train the model at our cluster, and then deploy it on your own system. And after you have done your training and you know how everything works, you can actually put your whole model. Oh, sorry. Excuse me. You can put everything into one file and then submit it via Slurm script, which is more elegant. But if you do it at the beginning, you might lose some core hours or waste core hours, because the job is maybe stuck, or we have to kill the job and so on. And then you submit the job, and then you can watch how it is going. So for training your models on the VSC5, just a few words on machine learning, deep learning, or any AI frameworks in general. Take your time for data preparation. Yeah. Test before you submit a big job in an interactive sessions like just shown before. I wouldn't recommend to mix frameworks. Use just one: TensorFlow, PyTorch, Scikit, or some other framework. If you have a big data set and you want to train it on our cluster, if they are bigger than 100 gigabyte, get in touch with us. We can help you. If you want to use multi GPUs, get also in touch with us. We can help you. And the landscape is changing very fast. Many big companies have their own versions of for example, the free library scikit-learn. Intel has boosted several functions which work better on their hardware. So everything is changing very fast at the moment. It's difficult to keep up. I can make a small live demo at our cluster, show how to submit the jobs. But since we are actually very late, I will just make it very shortly. Sorry. Okay, this is now already logged in. I'm logged in at the cluster. One can check the running jobs. On the cluster, you see several jobs are running. Not all of them are on GPUs. These are jobs which are queued. And I, in this particular case, I prepared just several files, which I then invoke in a, which I can invoke in a interactive Python session. You have to make sure that you have installed everything right and you have your TensorFlow in it and so on. So for this particular case, I need Python 3.9 at least, because TensorFlow needs it. And then so first, so I'm not on a GPU yet. So I for a interactive session, I can ask for a A100 GPU, and then you are put on a waiting list. Usually that goes fast, but sometimes it can also take some time. And then you can, like I showed on the slides, you can then work interactively on the GPU within Python or outside of Python. When you want to fine-tune a model or existing model, for example, a BERT model, then, like we already heard, there are several sources for pre-trained models. For example, Intel's Model Zoo or TensorFlow Hub, Kaggle. There is also another Model Zoo or Hugging Face, and then you choose your you choose the existing model, and then prepare the data, check the model architecture, and then do your hyperparameter tuning, and then your evaluation. Okay, so since we are, yeah, and just a few additional words. Fine-tuning a pre-trained model can be very powerful. We can use the same model architecture to new data sets, and but be careful, the data set should be similar to the original data set, and so on. Okay. Contact us if you want to use our cluster. Ask for a test project, and again, big data sets, get in contact with us, and for multi-GPU training as well. And since we are already over time, I would like to finish that. I am putting the GitHub GitHub folder where I will put a Jupyter script for this particular case with the codes, and then you can have a look. That my slides are already there, and with that I would like to finish. Thanks a lot.
Thank you, Zona. Okay, so we've reached the end of our webinar, and now is time for questions. We, of course, followed the chat during the talks and collected the questions. So I'm going to go through these questions, and of course, feel free to unmute yourselves if you have any other questions or if you want to add something. We have a question for, or actually few questions to Simeon, but about your first presentation. There was a question whether there is also information on the commercial use of large language models, and which of the mentioned licenses on Hugging Face would qualify for the commercial use.
That's a good question. As far as I know, there's no option to filter with that spec commercial use on the Hugging Face platform. It might have changed in the meantime, though. That's something that you could actually shout out to them to implement. That would be a great idea. But I'd go just for the generally well-known licenses like Apache 2. They're basically open for commercial use as well. Or the MIT license would be one of these. They're ones that you're actually safe with, let's put it that way.
Thank you, Simeon. Any additional questions on this topic? All right. Then we are going to continue with the questions to Sabine, and Simeon will come back to you later. I think that's reasonable. Sabine, I saw that you answered this question in the chat already regarding how one can technically make sure that the AI model abides by the GDPR. I mean, you answered it in your presentation, sorry. You answered another question in the chat, but I wanted to ask if you want to add anything on the topic of GDPR and AI models.
Yes, no.
Okay.
I think it really depends on the very specific application. And I strongly recommend to use one of the questionnaires to assess whether you potentially are developing a risky system that has to undergo this assessment of in the regulation. And then all of the inputs that have been given in the presentations of my colleagues are extremely helpful with regards to looking at biases, with regards to making sure that you have good data quality, that your model is appropriate, that you have enough data, etc., etc.
Thank you. Any other questions on this topic? Okay, there is a message in the chat, but I think it refers to, yeah, it refers to Zona's talk. Good. Then the message in the chat regarding the European value continuum was already answered by you, Sabine. And you wrote that the AI framework refers to the Fundamental Rights Charter and the values it is based on. If there are any additional inputs on this topic, please feel free to unmute yourselves and comment on that. If not, then I'm going to continue with the questions for Brian. Okay. Yes. So Brian, you received a few questions. So let's see. There was a question regarding why you didn't proceed with OpenAI, if the results have been better in the tests, or whether you did only test with ChatGPT 3.5 or also later releases.
We also tested later releases, and well, I'll just call them ChatGPT. ChatGPT is just overall better in Dutch. That's what we found. Comparing, of course, with these llama models. Why not proceeding with these? It's because, well, that was exactly our objective. We don't want to be subject to just OpenAI. We want to create language models that can be general and just for Dutch. But this was, I didn't mention it, but this was, let's say, a first attempt to see how far can we get, how much data do we have, and there were several parties involved, and we found that we can get somewhere, but it's bounded, and that's primarily it's not even because of the compute power, because as I said, because of these open source communities, we are able to train or fine tune slightly larger models nowadays, but it's really that data that we don't really have a hold of. We know that, for example, the Dutch National Library contains a lot of data, but it's really difficult to get hold of that because it's subject to a lot of copyright, and we don't really want to use that. So OpenAI, for example, has used data that we don't even know what the source is. Probably most of that data is copyrighted, to be fair. So it's purely a practical thing. We can just proceed with OpenAI and just use OpenAI forever, right? But in high risk situations in medical data, you don't want to use OpenAI because they get that data from you. If I use OpenAI's API right now and I input some privilege, so privilege data from a hospital, then they will obtain that data. Doesn't matter if they say that they won't use it in the future. It's just too high risk.
Thank you. Any other questions on this topic? Okay, then let's proceed with the next question, which is how did you manage to reduce the bias in the pre-trained Llama 2 model, and whether it would be possible to use another model in the post-processing step that filters the output of the original model?
Yes, that's certainly possible. That's also something that a lot of people are doing. It's also a technique to reduce compute power. You can first use a smaller model and then only use a larger model if it's necessary. So you have like a combination of models working together, figuring out when to speak, because this can be very compute intensive, especially if you have a few millions of users at the same time. About the bias, strictly speaking, we did not get rid of any prior bias that the llama models had, so they should be in there because we just fine-tuned those models on our data. And also something else that I would like to add that I did not mention is that the data that we use is also publicly available Dutch data. And since we don't know on what data these llama models are trained on, that data is so huge. It could be that we are just regurgitating that data again through the model. We don't know. I know that at least some sources of the data that we use, I'm quite certain that Llama hasn't seen that. And given our results, we can also say that there is some data in that the Llama model hasn't seen, but still, because it's not all open source, it's difficult to say what has it trained on, what does it know, what kind of biases does the model have. I know that there are some methods that you could apply, but these are very limited to try to get out, to try to remove that data. It's like memory deletion, you could say, but that it's always a trade-off between model capability and how much bias you get out of your model.
Thank you. So there was another question in the chat, which is connected to this one, right? Where someone asked if the benchmarking data sets that you mentioned were completely in Dutch, and if they are published or can be accessed for research.
Yeah, the benchmarking data sets were completely in Dutch, but they haven't been published yet. That's why I didn't cover anything, just that we benchmarked it.
Okay, thank you. And there is one additional question in the chat, namely whether your data cleaning or selection scripts are publicly available or will be available upon request.
They are not available, but upon request, yes, we can look into it. So if you want, you can mail me. I'll put my mail here. And then we can see what we can do.
Perfect, thank you. Any other questions to Brian? Remember, you can also unmute yourselves and ask the question directly.
Yes, I've got one question, please. If, let's say, we have some sort of machine learning ensemble model, which can then be used to classify histological specimen, to classify whether they are tumors in them or not.
Yes.
And then this ensemble makes a mistake and doesn't detect a tumor, and then the patient does not get the medical treatment they need. Who will then be liable? Who will be liable in the heuristic sense, in the legal sense?
Yeah, that's a whole active area of research, I would say, not just philosophically, but it's really difficult to trace back whose fault it really is. Is it the data annotator? Is it the model trainers? Is it the pathologists who just blindly followed the model? I think that I don't have an answer for you. There is no answer, I would say. I think that these models are not meant to replace anyone or any pathologist's final decision. They're always meant to assist. So if a histopathologist is if that histopathologist is diagnosing whether you're progressing to cancer, and it looks at the model's outputs to know to get more information out of that, then it's ultimately the pathologist's decision that gives you further treatment, for example. It's a tricky question, and I think it's one of the main issues that hospitals haven't applied these methods en masse, because it's really difficult. Even if we have evidence that these methods work 99% of the time, the problem is that we're all humans, right? And we all fall into that bias of just believing the computer. It's the computer computed this, so it must be right. And at some point, then you start relying less on your own expertise and your own experience. But nowadays, it's always and ultimately the pathologist. In the future, it depends on the trust that we gain on these models. But whose fault it is, I have no idea.
I mean, to be more specific, because you alluded to the problem that there are not enough personnel to classify those
Yes.
images, right?
Yes.
So if there is a classifying system, an automatic classifying system which pre-filters those specimens,
Yeah.
and then the pre-filter decides that something is definitely not cancer, but it is cancer, and it later turns out that it was cancer. Then no person decided that this particular image was having a cancer on it, right?
Yeah. I understand the concern. So a few years back, when I worked at the University Medical Center, and I talked with my supervisor about this, then he was. We used a neural network to assist him in some cases and to see how much time gain he got out of it. So it's not exactly that you have a bunch of data and then you're filtering a lot of that data, and then that the histopathologists never get to see that because they're filtered out of it. It's these images are just so big, they're gigapixel in size, they're not tiny images at all. So the histopathologist has to look through the image region by region and to see if there is any change in morphology or something suspicious that indicates some further complications. But the thing is that you could let a neural network check most of these regions, and then the neural network outputs, let's say, an estimate and a uncertainty. And using that uncertainty, then the pathologist can make a decision out of that. But he doesn't have to go through the data 100% fully, but not in the sense that you mentioned, but in the sense that his process can be sped up, but he will never skip a data point because the algorithm says that there is nothing there. But as I said, we're all human. Maybe at some point we become too reliant. Again, I have no idea who would be at fault. I think that would be the hospital in the end if somebody turns out to have cancer but has been skipped completely because of this.
Thank you so much, Brian. Any other feedback, comment on this topic, or any additional questions? If not, I have a question, namely whether or not you can artificially increase your training data with data augmentation, for example, with synonym replacement.
What do you mean with synonym replacement, for example?
We're replacing. Yep.
Yeah. I actually had this question. So basically, if you enlarge and synthetically enlarge your data set by just using other words, which you could use a model for, and increase the data set that you have of the Dutch language. Is this something that you looked into, or?
No, we didn't look into that, but I know of these techniques, and they can give you some performance boost, but it's never that much. It's always like marginal, and that it also depends on what kind of regimes you're looking at, because I looked at the Dutch language, which is not exactly the language with most data, but it's also not exactly an African language where I cannot not find anything. So, well, fortunately for us, then we live in this regime where we have enough data that we don't have to synthetically augment our data sets. In essence, one thing that we could have done is just keep, for example, all the Twitter data and or other sources like Reddit data, but we saw that that brought a lot of negative bias with it, but the models were more expressive. But that's not what you want. Yeah, I know that, for example, with very small languages, so some African languages, or maybe let's say a language from Papua New Guinea or something, there are some techniques that you can use to speed up the language modeling training process. There is a whole subfield that's called meta learning, where you try to do that, and I've seen some papers where they do find like this performance boost with just a few examples shown. And that has to do with how languages are connected together, like syntactically or even semantically. So you could have a language from India, but if you train your language model only on Romance languages, for example, then you can have a big boost by just training on a few data samples from a very niche Indian language. It sounds very counterintuitive, but the performance boost is not that big. But in the case of that tiny Indian languages, it is a lot because there is not much data for that language. But no, we didn't look into this because we have enough data, but not enough.
Yeah, I see. Yeah, thanks.
Thank you. There is another question in the chat. I'm not sure who this question is directed at, but I'm just going to read it out aloud and feel free to answer. So what about training large language models on encrypted data? Whether any one of you has any experience with this?
No, I don't have any experience with this.
Me neither.
No, that would be something we'd need to shout out in the EuroCC network. Yeah.
Okay, then I'd like to circle back to Sabine for a second, because we have 2 additional questions for you. And then we can go back to Simeon and the EuroCC accelerator. So you mentioned use of subliminal techniques. And we were wondering whether this includes like recommender systems or marketing in general.
Yeah. No, it does not include this in general. So recommender systems can be very, very transparent. And particularly when you have as a potential user the possibility to set, for instance, the criteria for the recommendations. They can be manipulative in case these recommender systems use information that are meta behavior, like your clicking behavior, that you are not aware of, and that might guide you in certain directions that might not be truly reflecting your preferences, but rather the interests of the company using the system, right? So that's the problem, right? If there is, for instance, a study that shows that, for instance, Amazon, not Amazon, sorry, the Google algorithm for, if you ask in Google Maps the distance, how long it takes to go from A to B, right? It has been shown in papers that it overestimates the time you need when you go by public transport and underestimates systematically the time you need going by car, and then offering transport services And here, in this case, for instance, would be manipulative, because it would kind of guide you into the direction to use a car instead of public transport. And of course, Google then caches when they sell certain transport possibilities, like taxis, or and this is manipulation, right? So it is not about learning from users' behavior, the preferences they have, as long as it is transparent and truly reflecting the preferences, and it is not manipulative. Did that answer the question?
Yes, thank you. And then we were also wondering if it's possible that, for example, a regulator within the European Union decides that, I don't know, a Wikipedia entry is like, I don't know, not how to say this, in line with some regulation or something. Would we then have to retrain our models, which have been trained with data from Wikipedia? Or how would we handle such exceptions?
Well, what you would have to do is you would have to show that your model is not, for instance, discriminating anyone, right? Is not including discriminatory biases. You would have to demonstrate that. And of course, you would have to demonstrate what you have done in order to make sure that this happens, right? And if you use data that has clearly been proven to include certain biases, and you use that to train your own model, then you have not been very careful, right? So that's the point. But if you say, oh, well, I have used this type of data, and I have cleaned the data as demonstrated by our colleague Brian, right? Then you need to be transparent about how you safeguarded human rights in your model. And of course, as Simeon said, there might be still implicit biases in the data, which we don't know because they're so implicit that we can't, we have to be made aware of it, right? So this could also all happen, but what we try to do is to mitigate the risk as much as possible. And so you need to be transparent about how which data you use, how you cleaned it, what you did to mitigate biases, etc. And so with regards to Wikipedia, yes, very likely there are biases in there. So, yeah.
Thank you. Yes. Okay. So, Simeon, there are 2 more questions left for you. And I'm going to start with the second, which is whether there is any way to test or track if the attention heads are learning different things. For example, one head is learning about verbs, one knows about declination, etc.
That's a good question. I would say you could basically trust that they're learning different things simply due to the fact that the weights of the word representation matrix, or how this word representation matrix came about, have been initialized differently. So they're different from the point where you actually start. And then I would also assume strongly that they learn different things because these word matrices are broken down into subspaces. So basically each head looks only at a certain subspace, at a certain reduced dimension with reduced information, and that information is different to what the next attention head looks at. So I would almost say, yeah, I trust that these things are different. However, they're very abstract, and you couldn't actually say that's just for us to imagine how this works, that they actually differentiate between certain aspects of the language that are clearly separate to us humans. What you might be able to do, but I have never done that, so I'm not quite sure, but you could set a callback with a cosine similarity function, simply to check whether these matrices that come out of the attention head are actually different, or get a grasp of how different they are on a scale between 0 to 1. Yeah.
Perfect, thank you. And then there was a question regarding compute power and the cost of compute power, namely how much the Vienna Scientific Cluster would charge for a certain amount of computing power. And I'd like to share my slides again just for you to see the contact details for EuroCC Austria, because in Austria we would be the contact person if you have questions on this topic, but Simeon, you may want to comment on it.
Yeah, basically the way we go about it is we offer you an account if you are from a company that has an interest or a need for compute power. So basically you can just have a test before invest, have a proof of concept, whatever you call it. It's quite leger the way it's handled in Austria, but we can give you 100,000 core hours. That's not the problem. So you can actually find out if your problem is workable for HPC, if it's parallelizable, and you could get different supports and courses along the way until you're ready to use it in earnest. But yeah, if you need more time, then you can easily talk to us. Depends how much. If you use it on a regular basis, however, we do have a price list simply to cover the operational costs. So we don't make a profit with that, but it's basically we just try to cover the energy costs, which are quite high. If you are interested, we could send that to you. I can't quote each because it depends on which CPU, which GPU you request. We have different pricings for that. And if you go to the really large scale machines in Europe, they're free of charge. However, you have to apply to them. You first have to prove on the VSC, for example, that your problem is scalable and needs more compute power. And you basically apply for that. We can help you with that. This goes through a peer review process, but then we get access to the really large machines, world-class machines. Yeah, and they are free of charge.